For decades, the medical community defined autism spectrum disorder through a lens of rigid psychiatric symptoms. That definition is evolving to reflect a biological reality. ASD is driven by dynamic metabolic processes cascading across the central nervous system. Traditional interventions have historically focused on downstream symptom management, prescribing medications to suppress anxiety or irritability without addressing the underlying cellular pathophysiology. A shift in this regulatory approach arrived when the FDA initiated approval for leucovorin calcium tablets. Leucovorin specifically treats cerebral folate deficiency. This targets the biological source of the autistic features, a departure from traditional efforts to mask outward behaviors. An investigational compound called L179 represents the next step in this evolution. Recognizing its potential to target core metabolic mechanisms, the FDA granted the drug Fast Track designation. The FDA's validation of these metabolic pathways establishes a new regulatory standard, mapping ASD behavioral phenotypes to discrete enzymatic mechanisms. The clinical relevance of L179 was tested in a 40-patient Phase 2A safety and dosing trial, utilizing a double-blind randomized architecture. Researchers tested multiple daily dosing regimens to establish a therapeutic window. The efficacy data focuses specifically on the outcomes of the 600 mg daily cohort. This line chart recreates the Phase 2A aberrant behavior checklist data. Over 28 days, a clear downward trajectory appears for the treated group against a flat placebo baseline. Concurrent drops were also recorded in ADOS and CGI severity metrics. Looking at this stacked bar graph of the social responsiveness scale, we see distinct categorical shifts. Patients moved from severe and moderate classifications down into the mild categories. These rapid, multi-domain improvements suggest L179 addresses a core systemic dysfunction, reaching beyond the suppression of isolated neurological symptoms. Traditional pharmacological treatments for ASD, like risperidone, target specific postsynaptic receptors. Because they only block the receptors at the end of the chemical sequence, they yield heterogeneous results and incomplete symptom coverage. First, to fully understand how L179 operates upstream, we have to look at an enzyme called tyrosine hydroxylase, or TH. TH is the singular rate-limiting enzyme responsible for the entire catecholamine biosynthesis pathway. In a standard biochemical progression, L-tyrosine enters a synaptic terminal and is converted by the TH enzyme into L-dopa, then synthesized into dopamine and norepinephrine. L179 acts as a competitive presynaptic inhibitor. It physically locks into the tyrosine hydroxylase enzyme, completely blocking the conversion. This upstream blockade acts as a broad-spectrum downregulator. By entirely shutting down the biochemical factory at its source, L1-79 simultaneously throttles the synthesis of all downstream catecholamine neurotransmitters. The immediate physical consequence of this blockade is that presynaptic neurotransmitter vesicles progressively empty their internal chemical payloads into the synaptic cleft without being resupplied. By tying off supply at the enzymatic bottleneck, L1-79 resolves systemic hypertone while bypassing the receptor-level side effects common in psychiatric medicine. Modulating catecholamine tone presents a specific dosing challenge. Clinicians must maintain stable blood serum levels without inducing dramatic pharmacological peaks and troughs. This pharmacokinetic curve demonstrates the limitation of the standard L enantiomer of alpha-methylparatyrosine. It has a rapid metabolic clearance, resulting in a sharp spike and steep drop-off with a half-life of only 3 hours. To solve this, L179 was formulated as a racemic mixture of the compound. This structural design alters the drug's metabolic absorption profile. The racemic formulation quadruples the half-life of the drug, generating a smooth curve that extends across a 12-hour timeline axis. This extended half-life clinically translates into a highly viable twice-daily dosing schedule, an essential parameter for pediatric and adolescent populations. Engineering a 12-hour half-life transitions the compound from a theoretical biochemical probe into a practical, sustained therapeutic intervention for ASD. The effects of this intervention are not limited to the synaptic cleft in the brain. Autism spectrum disorder is highly comorbid with gastrointestinal dysfunction, directing focus to the enteric nervous system. Physiologically, nearly 46% of the dopamine in the human body is synthesized directly in the stomach, pancreas, and duodenum. This region is heavily influenced by propionic acid, or PPA. PPA is a short-chain fatty acid from altered gut microbiota digestion, frequently found in ASD patients. Excess PPA moves from the gut lumen into the bloodstream. Here, it acts as a systemic transcription modulator. Once inside a target cell, PPA physically elevates tyrosine hydroxylase mRNA levels. It commands the body to overproduce the TH enzyme. This gut-driven enzymatic overproduction creates a systemic surge of catecholamines. The overproduction saturates both the peripheral and central nervous systems. The neurological symptoms of ASD are, in many cases, downstream manifestations of an upstream enteric metabolic feedback loop gone awry. Massive releases of enteric dopamine directly regulate and increase the local production of bile salts in the gastrointestinal tract. When localized bile salts are elevated, they degrade epithelial integrity by physically forcing the cellular tight junctions to separate. This permeability creates a leaky gut mechanism where incomplete digestive products and additional short-chain fatty acids flood into the systemic circulation. This flood crosses the blood-brain barrier, where bile acids act as neurosteroids that inhibit GABA-A receptors. This disrupts the inhibitory postsynaptic potentials required for cognitive balance and alters the mesocortical limbic reward circuitry. Because the resulting ASD behavioral phenotype is driven by a self-amplifying systemic loop, isolated CNS receptor blockers will fail. Only a systemic TH inhibitor, like L179, can break the cycle at its source. To validate this model, an expanded Phase 2b clinical trial is currently underway across leading national research centers. The trial utilizes a 50-patient ABBA crossover design, testing the optimized 400 to 600 mg twice-daily dosing regimen identified in Phase 2a. This chart demonstrates the critical new primary endpoint for this trial, growth scale values. Standard scores often flatline and mask developmental progress in ASD patients. Growth scale values accurately isolate and measure the true rate of novel social skill acquisition over time. Restoring metabolic homeostasis with L179 is designed to allow these developmental trajectories to resume by removing the catecholamine bottleneck. The future of ASD therapeutic development relies entirely on identifying, targeting, and correcting the precise enzymatic pathways driving the disorder's root metabolic